Hi, welcome to the introduction video on acids and bases. This is part 1 of 2. As you watch this video, be sure to fill out the notes in your note packet. In this video, we're going to cover what are acids and bases and how do they react. So let's begin. So before we define acids and bases, it's a good idea for you to get a sense of what they look like. Let's start with acids. Acids you can recognize from their chemical formulas, like the ones shown in the examples at the bottom. Acids you can recognize as having hydrogen in the front or a Cu group in the back. So if you look at these first 4 examples, you'll see hydrogens in the front of their chemical formulas. And in the last example, which is known as acetic acid, also known as vinegar, you have the COOH Cu group in the back. The structure of the Cu group is seen here, so you can take a look. You see carbon with an oxygen double single bond, a carbon oxygen single bond, and a carbon oxygen single bond. This oxygen that is singly bonded to the carbon also has a single bond to a hydrogen. And these hydrogens that you see here in the Cu group and also the hydrogens you see here are important because they are what make an acid an acid. So to talk more about acids, let's look at the structure of acids. We can divide acids into 2 types, binary, and those are ones made with 2 types of atoms, for example, HCl and H2S. And the hydrogens in those are highlighted in red because, as I said, which we'll see in a moment, it's the hydrogen that makes an acid an acid. You also have oxyacids, and those are acids that come from polyatomic ions. If you remember the polyatomic ions like sulfate, nitrate, phosphate, phosphite, etc. Acids that are made from those ions are called oxyacids. And the key thing with these acids, if you know what the polyatomic ion is, you can determine the chemical formula of the acid based on the fact that the number of acidic hydrogens, we call these special hydrogens here acidic hydrogens or acidic protons, those hydrogens, the number of those will equal the amount of negative charge. For example, if you have something like nitrate, the corresponding acid to nitrate would have 1 hydrogen, would have 1 acidic hydrogen, and you can tell because nitrate has a -1 charge. So the corresponding acid will be HNO3. Whereas something like sulfate, which has a 2- charge, would have 2 acidic hydrogens. And acetate, which we have already seen, its corresponding acid here would have 1 hydrogen. Okay, now that we've seen what acids look like, let's take a look at bases. Bases are either metal hydroxides or amines. An amine is a chemical made of a nitrogen with 3 things singly bonded to it, and usually the things that are attached to it through single bonds are hydrogens or hydrocarbons. Hydrocarbons, remember, are chemicals made up of carbon and hydrogens. So let's take a look at some example. For the metal hydroxide bases, we have sodium and calcium hydroxide shown here. And these are ionic compounds, so their Lewis dot structures have brackets and charges. There are 2, we also have 2 examples of amines. This is ammonia, which is used in cleaning. And this one here is diethylamine. And you will notice that in the amine structures, the nitrogens have a lone pair, and that's super important if it's going to be an amine, and then 3 things attached to that nitrogen through single bonds. So just to summarize, we have 2 types of bases. They're metal hydroxides and amines. All right, now that you know how to recognize an acid or base from their chemical formula, you're going to identify each of these things as acid or base or neither. So you should pause this CFU, and then when you press play again, the answer will be revealed. Okay, so let's start with identifying some bases here. KOH and calcium hydroxide are bases because they're metal hydroxides. Here we have 2 amines. Those are bases. Now let's look at some acids. We have these acids here with hydrogens in the front. And then we also have 2 acids here with Cu in the back. Remember, hydrogen in the front, Cu in the back is an acid. KNO3 is a salt. It's neither an acid or base. And C2H5OH is a alcohol. It's neither an acid or a base. Nitrate is neither an acid nor a base. And water, we'll find out later, actually can act as both an acid or a base. So in water, the one hydrogen can act as that acidic hydrogen that you will see in acid, and then the OH group can act as the hydroxide that you see in a base. Okay, so now that we talked about how to recognize them, what are the definitions of acids and bases? Really, they're defined by their chemical behavior. There are three definitions that are used to describe acids and bases. Lewis' acid and base definition involves donation and acception of electrons, and that's sort of the broad definition. And within that definition, there are two types, Bronsted-Lowry and Arrhenius. Now, although Lewis encompasses both of those, truly only organic chemists use Lewis as the definition, so we're actually not going to follow that, but you may see that in the future. The two definitions we're going to follow are Bronsted-Lowry and Arrhenius. So let's start by taking a look at Arrhenius. Arrhenius definition has to do with what happens when an acid or base is dissolved in water. For acids, when it's dissolved in water, they release protons. And you can see that here with this example of HF, hydrofluoric acid. When hydrofluoric acid dissolves in water, it ionizes or breaks apart into ions, things with charges, into H plus and F minus. And again, it's this proton, this H plus, that makes it an acid. Acetic acid also does the same thing. So this is a Cu acid or carboxylic acid. When it is dissolved in water, it breaks apart into H plus, and then its corresponding acetate. Bases, on the other hand, when they're dissolved in water, they break apart into hydroxide. So you can see that with metal hydroxide, like calcium hydroxide, as shown here. And when it dissolves in water, it breaks apart into calcium and then the hydroxide. However, what about something like NH3, which does not have an hydroxide, and amine does not have an hydroxide? So this definition, Arrhenius, falls short when it comes to amines because you don't see where the hydroxide comes from. It doesn't just ionize into a hydroxide. So we'll have to look at the Bronsted-Lowry definition, but before we do that, let's see what actually happens to NH3 when it does dissolve in water. So NH3 is a base, and it will react with water to form ammonium hydroxide, and that's this species here. So when we think about NH3 in water, we should actually be thinking about NH4OH or ammonium hydroxide, because that's what's really undergoing reactions for NH3. With that being said, let's go now into our second definition, which is the Bronsted-Lowry. As we said, Arrhenius doesn't apply for NH3 because NH3 in and of itself does not have a hydroxide. Bronsted-Lowry definition has to do with what happens when acids and bases react. So for an acid, when it reacts, it donates a proton, and a base will accept a proton. So here we have our acid HF and our base NaOH. The proton in the acid will undergo a double exchange reaction with the hydroxide, forming water. So they basically switch partners. We've seen that before. And then the sodium and the fluorine will switch as well, forming a salt. So this is what's called a neutralization reaction. We have an acid and a base, makes a salt and a water. And we can see from this reaction that acids will donate a proton and bases will accept that proton. And in doing so, the acid and the base will form a water. In addition, the sodium or the metal ion and the non-metal ions will form a salt. And here are just a few examples so you can see that exchange. Okay, so now that we've talked about definitions, let's think about what comes to mind when we think about acids and bases, so we can start talking about some of their properties. All right, so acids, here's some things that may come to mind when you see or hear the word acids. And perhaps these are some things that may come to mind when you hear or think about the word base. And that's because these are all examples of acids and bases. So let's talk about some properties of some things we may already know. Starting with what we now know based on the definitions of acids and bases, acids will produce H plus in water and bases OH minus. We can recognize acids and bases from their formulas. So hydrogen in the front, Cu in the back is an acid. And if you're dealing with a metal hydroxide or an amine, you know you're dealing with a base. But what about some properties? So some properties like taste, acids will taste sour and bases will taste bitter. So that's why when you think of acids, you may think of acidic fruits like citruses, and they have a sour taste. Acids also break down metals, whereas bases break down fats in a process called saponification. And if you are into soap making, that's the same reaction that you do when you're making soap. So you start with a fat and then you add some sort of base to it. Another thing about acids is that they're corrosive and poisonous to skin, whereas bases will feel slippery. So if you ever accidentally spill bleach on your skin, you'll notice that it starts to feel slippery. And that's actually because the bleach, which is a base, is reacting with the fats or oils in your hand to produce a soap. So that's why they feel slippery. Final thing about acids and bases is that they have what's called certain pHs. So acids have a pH less than 7 and bases have a pH greater than 7. So these are some important properties. You want to pause this video at this moment and fill in those properties. Let's take a look finally at the pH scale. So we mentioned that acids and bases have certain pHs. So let's talk about what that is. pH is a scale that is used to measure how acidic or basic something is. The lower the pH, the more H plus ions that are in solution, so the more acidic. And the higher the pH, the less H plus, or the more OH minus ions are in solution, so the more basic. So as your pH decreases, you're dealing with a more acidic solution, and as it increases, you're dealing with a more basic solution. So pH less than 7 is acidic. pH equal to 7 is what's called neutral. That means you're neither an acid or a base. An example of something that's neutral will be plain water. And pH greater than 7 will be basic. How do we measure pH? We measure pH using what's called a pH meter or pH paper. So a pH meter is just a probe, and you'll stick it in whatever solution you're dealing with, and then it'll give you a digital reading of the pH. So here, this is clearly an acidic solution because the pH is less than 7, it's 2.66. For the pH paper, what you do is you take out a strip of pH paper and you dip it in your solution, and then depending on the pH, it will change color. If it's neutral, it'll stay about the same color, but if it's acidic, it'll be sort of a red, orange, ish sort of color, and if it's basic, it'll go somewhere between green and purple. All right, so what you're going to do now is you're going to try this CFU to identify whether the solution is an acid or a base. Press pause, and when you press play again, the answer will be revealed. Okay, so A is a base, and that's because it turns the pH paper purple. And B is an acid because, as you can see here, the pH is 2.86, which is less than 7. Last thing we'll talk about is acid and base neutralization. So when acids and bases react together, they neutralize one another, meaning that they bring their pH closer to the neutral position of 7. And acid and base neutralization results in a salt plus a water, which we just saw before earlier. And again, that's an example of a double displacement reaction. So in your notes, be sure to write down the acid and base yields a salt plus a water. That's something that you need to memorize. Here are some examples of acid and base neutralizations. All right, now you're going to pause the video and try this CFU, see if you can predict the products of acid and base neutralization. For a hint, you might want to underline the hydroxide in the base and the proton in the acid, because those are the things that are going to exchange, remember, to make water. Okay, so here are the answers. We also had to balance the equation. So for C and D, we added some coefficients to just balance the atoms on both sides of the equation. All right, that's it for part 1. Part 2 is next.